time for another proof. Time for some more rockin' music. Okay, so let's pause on that Midsummer Night's Dream and have a look at. So this is the same theorem that we saw in the previous one. This is still tan chord theorem that we're looking at. But because the diagram looks a little bit different, because we've got an obtuse angle, we're still showing that the angle between the tangent and the chord is equal to the angle in the opposite segment. But now when we do our construction, so we're going to do exactly the same construction. We're going to construct our radii over here, and the version of the proof we're going to look at. Remember, there are kind of a few ways to prove things, and, you know, let's stick with this one. And we're still going to say, well, if we do that, we've still got a 90 degree here. But now this angle is an obtuse, it's not kind of 90 minus x. So in this version, I'm going to let this one equal x. We're still going to have an isosceles triangle. And we're still going to find this angle here, which is 180 minus 2x. And therefore, we're going to find this outside obtuse angle to be 180 plus 2x. And therefore, this angle over here is 90 plus x, angle at center. So the idea still follows the other one, but it just looks slightly different. So worthwhile redrawing and doing. And, well, this whole angle on the outside over here is 90 plus x. So we've shown it. So that's going to be the essence of what we do. So let's just capture. I'm going to leave all that stuff written, and maybe I'll just highlight the bits as we go. So first of all, we constructed our I'm getting worse at writing the word construct. Our radii, OP and OB. OP and OB. And let's say that OPE is, let's go, OPE equals 90 degrees tan rad. I know we can kind of incorporate that in the next statement, but I think it's useful. It's just kind of it's a separate statement. And then this angle here, P, I'm going to call it P1. So P1, we're going to let that equal x. Therefore, B1 is also x. Now, you don't have to do it with x's, but I think it's a lot easier to kind of keep track of which angles we're dealing with here. So we got B1 is x. Reason is because we've got yet another isos triangle with those radii haven't been drawn. Okay, so this angle here, O in the middle here, and I'm going to kind of fit a little 1 in there. O1, not very great. If I wrote BOP, I guess I could write obtuse, but so that angle, not the reflex angle, the one on the right, is 180 minus 2x because of sum of angles in triangle. Okay, so that's that. So therefore, the other angle, maybe we can call that reflex O, is 180 plus 2x. Because when you add them together, it's a revolution, or it's sum of angles round a point. So let's move across there. So I always got angles round a point, even though it would be quicker to write revolution. Okay, so we got 180 plus x, so therefore D, there's only one angle over there, D equals 90 plus x because of angle at center, and you already know I'm just gonna kind of 2 times angle at circumference. Okay, and well, therefore we've shown that this angle here, BPE is equal to angle D, because they're both 90 plus x. Because if you see here, this whole angle here is 90 plus x, and this one here was 90 plus x. So there we go, 90 plus x, 90 plus x. It's also why I like to, you know, this time I went for 90 minus x in the previous proof, because then it kind of, they match up nicely. So that was that.